All right, we're back and we're in chapter 21, I believe. 21, we're going to do a little bit different. We're going to talk about acids and bases, which the chapter does. And then it talks about oxidizing and reducing. We're going to skip that part. Oxidation and reductions are important reactions, but they're kind of complicated, not very obvious, and I would rather talk about the other main 5 types or groups that all kind of chemical reactions go into, and I think that will be a more useful thing for you in everyday life, whereas the oxidation reduction, although that has a lot to do with electricity and a whole bunch of other things, is a little more complicated and not quite as useful. So let's talk about acids and bases first. We're all familiar with the idea of acids and bases. Possibly, if nothing else, in a movie where the villain is putting the hero or the heroine over a vat of acid and threatening to drop them into it, or eats people's flesh away and all that sort of thing. Unfortunately, acids aren't really all that exciting most of the time. Your skins are fairly resistant to acid, although there are a couple kinds you wouldn't want to be dumped into. But what are acids and bases, and why are they important, and why does it make such a big deal? All right, let's look at some things. So first of all, let's talk about acid first. The word acid comes from a Latin word, just like a lot of our other words, and it comes from the word acidus. And acidus basically means sour. Okay, and so acids are chemicals that have a sour taste. Okay. Citric acid, probably the one of the most common flavorings in the world, period, and that is made from, usually it's found naturally in oranges and lemons and other citrus fruits, but that's where that sour taste comes from. Now, oranges have a lot more sugar, so they taste sweet, but they still have a tart sourness to it. Vinegars and other, but basically acids have a sour taste. Besides having a sour taste, they are also usually very reactive with metals. Once again, your skin, not so much, except for some, like nitric acid, that attack proteins, in which you have in your skin. But since you have very few metals in your skin, that's not usually an issue. All right, so but they do attack, and most metals are fairly highly reactive with metals. And this is one reason you do not see acids in general used as cleaning products. They would really get after stuff, but unfortunately they also attack pipes and metal fixtures or faucets and things like that. And so we don't use them too much. About the only acid that's used for cleaning supplies is toilet bowl cleaner. Why? Because toilet bowl is usually porcelain or plastic, and therefore the strong acid will not really attack it. All right, but what it is, an acid, that doesn't really answer our question, does it? All right, so let's talk about it. Well, if you have an acid, like this is hydro, because you got the H, hydrochloric acid, or using the rules we did earlier in the year, you would just say it is hydrogen chloride. Either one would be acceptable. Acids have a special naming thing, so that's why it's hydrochloric acid. But if you said hydrogen chloride, people would know what you're talking about, at least chemists would. This is an acid. Well, basically, when you put acids in water, all right, if you put acids in water, they basically release hydrogen ions. Now, how's that different than a hydrogen atom? Remember, ions have a charge, so they give little H positive ions. So, for example, if I put HCl in water, it would separate into hydrogen ions and chlorine ions. Okay, and these loose hydrogens are what make it an acid and what make it very reactive. If you remember, the formula for hydrogen is 1 proton and it has 1 electron. So that's when it's neutral, but if it has a charge, basically that means it's a positive charge, so that means it got rid of its electron. So instead, what you would have is just 1 proton floating around. So really, when we talk about a hydrogen ion floating around, it's the same thing as one proton floating around. So if you have this proton floating around all by itself, guess what it's looking for? Well, it's looking for a negative that it can rip out. And if it starts ripping electrons out of something, you have all these hydrogens in an acid, and they start ripping all the electrons out and destroying something. That's what we call corroding. And so that's why they're very reactive, because you just have these bare protons floating around all by themselves. All right. Now, since we're in water, though, and the formula for water is H2O, I usually just put hydrogen ions like this, but a lot of times this hydrogen will grab onto one of these water molecules. Okay, so now instead of two hydrogens, now you have an extra one. So sometimes you will see acids written as, instead of things that have H positives, you will see where it has an H3O positive. Okay, so it's like water with an extra hydrogen. So now it has a charge. And basically, either one of these are the same. I prefer using the H positive because it's more obvious, whereas this one's a little more confusing to people. But either way, you'll see it in the book, H3O positive. That's the same thing. That's called a hydronium ion, because it's water plus an extra hydrogen. But basically, that's the same thing as a hydrogen ion floating around by itself. Okay, in the water. So if it combines with water, it makes a hydronium atom. But it's still the same thing. It acts like hydrogen. It has an extra proton floating around that wants to react with something. Okay. Now, because they give off hydrogens, or which are basically protons, acids are also known as proton donors. All right, proton donors. And so they are donating, or they give off, they have these free protons that are floating around and want to go off and do things, attack things and stuff like that to corrode. There are a couple of ways that we refer to how strong or powerful an acid is, and I want to talk about some of the differences between that. Okay, and so we want to talk about what's the difference between a strong and a weak acid, and then we'll talk about whether it's dilute or concentrated. But let's start with strong or weak. All right, we said that something is an acid if it gives off hydrogens when you put it in water. Okay, for example, this is HCO3, or carbonic acid, carbonate. So it's hydrogen carbonate or carbonic acid. Okay, and if you look at these, some of the hydrogens have come off. All right, but a lot of the hydrogens have not dissociated, which is just a fancy word of saying separated off by themselves. So if few hydrogens have dissociated or dissolved or should be only one S there, sorry, my bad, but dissociated. If very few of them have come off, then we would say this is what we call a weak acid. Okay, and therefore it's never going to be very strong because there's not very many hydrogens, therefore it's not very acidic. Okay, so it would be considered weak, and very few of these have separated off, and so that no matter how many of these you put in here, there's still going to be a relatively low number of them that come off. Percentage, say 20% or whatever. Okay, now on the other hand, this hydrochloric acid is what we would consider a strong acid. All right, if you look at a strong acid, you will notice that we have shown every single hydrogen has come off. Maybe not in every strong acid will every single one come off, but if almost all of the hydrogens come off, then that would be considered a relatively strong acid. Okay, even if you just had a few hydrochloric molecules in the water, almost every single one of them would come off, and that is considered a strong acid because they've almost all dissociated. So it's very acidic because all the hydrogens that are possibly come off have come. Now, most acids fall somewhere in between. I mean, they're not every single one going to come off of hydrogen dissociate, but on the other hand, they're not all going to stay together. So we would say something's a relatively strong or weak acid depending on how many of the hydrogens have come off. So it's kind of a continuum between these two. Okay, and most acids are going to fall more toward one end or the other, and there's some that probably fall about in the middle. All right, but that's the difference between a strong and a weak acid. It really has to do with how many hydrogens have separated and become ions in the solution. The other thing that affects how powerful an acid or a base is depends on how concentrated or dilute it is. If we took this same amount of carbonic acid, which we already know we would say is a weak acid, okay, because it doesn't separate very much, and we put it in twice as much water, okay, and we still have, and then you still have all the other HCO3. I'm not going to write all of them on here, but you get the idea. All right, they're all still here. All right, and if now we have twice as much water, but the same number, 2 hydrogens that have separated, which one is going to be more powerful? Well, the more concentrated one would be up here. Concentrated acid or bases. Okay, if it's concentrated, that means there is less water for a given amount of acid. Now we would measure that in moles, molarity, and molar and stuff like that. We're not going to worry about that. Just know that if there's less water for a certain amount of acid, smaller amount, like up here in this one, then that's going to be considered more concentrated. If you water it down by adding more water, now there's the same amount of acidic ions, H positives, but they're spread out over a bigger amount of water, then they are going to be more diluted. Okay, so diluted acids have been basically watered down, so there is more water for a given amount of acid. Okay, so basically concentrated or diluted has to do with how much water has been mixed with it or not. Okay, and that basically what it has to do with. Now, is it possible to have a strong acid that is weaker than a weak acid? Well, it might have less of an effect if it's been watered down so much. If we took this strong acid but poured it into a swimming pool of pure water, it's been so diluted you won't even notice it's there. Okay, a lot of pollutants are kind of like that. There's so few of them that you really don't notice they're there. Okay. On the other hand, we have a weak acid, but if it's very concentrated in a small amount of water, then it may actually have more ions and therefore be more acidic than a strong acid that's been diluted down, like that swimming pool full of this other acid. Okay, so both of those have to do with how powerful and how effective or whatever, how much it will react as an acid or a base. But watering it down has to do with concentrated or diluted. How many ions, hydrogen ions, separate has to do with whether it's strong or weak. Now we'd like to talk about bases. All right, how are bases? We kind of tend to say that bases are the opposites of acids in a way, and that's kind of true. They're not exactly just opposites, but they are pretty much. All right, bases. Okay, sometimes you will hear the word alkali. We'll talk about that in a minute, or alkaline. Okay, but bases, unlike the sour taste of acids, have usually more of a bitter taste. I don't recommend eating most of them because a lot of them are cleaning supplies and would be kind of deadly that way. But the other characteristic is they tend to feel very slippery. All right. If you ever get bleach on your hand and rub it together, it's very slick and it's hard to wash it off. It feels like it wants to stay on your hand, so it's very difficult to get rid of, but it's very slick. So one of the main things, if you're in a lab, if you spill base, not only is it the danger of a strong base on the ground that you could fall in and bleach out your clothes or possibly corrode your skin or do other things to, is the fact that just that it is so slippery, it's very easy to slip on it, so it just makes it a little more dangerous. Okay, and the easiest way to look at a base is that when you put them in water, they release not hydrogen ions, but hydroxide ions, which are OH negative. Okay, and we talked about that. We're naming things. We talked about OH means hydroxide. So it releases these hydroxide ions. All right. Now, OH, it wants to receive hydrogens, so sometimes they are called proton. Remember, one hydrogen ion floating around together is called that. So these are called proton sorry, acceptors. Okay, because they want an hydrogen to join with them. And think about it, if you put a hydrogen with it, what would it become? Well, we'll have to answer that in the next video, but think about it.